Bismillahirrahmanirrahim. Assalamu alaikum. In our today's video, we will discuss about root locus technique. The variation of system parameter K varies the transient response and the stability of the whole system. So if we find the closed loop transfer function for this system, we get this value, this second order system. So if we change the value of K from 1 and then we'll take second value 10 and third value 100, we see that for K equal to 1, the nature of response is overdamped. The transient response is very slow. If we increase the gain K and make it 10, we get the underdamped response. The response gets its value at approximately 4 seconds. And if we further increase the value of K, the response has ripples in the transient response, and again it has fast transient response. So we can see that by varying the system parameter K, we can change the nature of transient response. Again, if we start the value of K from 1 and gradually increase it, we can see that poles has overdamped, the nature of response is overdamped, and again at 2 it has overdamped. At exactly 2.25 the response will be critically damped, and if we increase the value of K from 2.25, the response become underdamped. So for the lower order system, like for second order system, we can manually or calculate the nature of response. But if the order of the system is higher than 2, it will be difficult to find these pole location. So we will use the root locus technique to find out how the pole vary with the system gain. The closed loop poles of the feedback control system are the roots of the characteristic equation. This is characteristic equation. The roots of this equation are the closed loop poles. The root locus is the path of the poles traced out in S-plane as system parameter varies from 0 to infinity. As we change the system parameter K, the response changes, and from starting from 0 to infinity, how will the pole will move in the S-plane? This will give us the root locus. Root locus is a graphical representation of the closed loop poles as system parameter is varied. It provides a qualitative description of the system performance. For feedback control systems, it is difficult to comprehend from a qualitative point of view, and as they rely heavily upon mathematics. The root locus that we will cover in next slides is a graphical technique that gives us the qualitative description of control systems performance, and also serve as powerful qualitative tool that yields more information than the methods already discussed. It provides solution for the system of order higher than 2. For order 2, we can find the root locus manually, but for higher order, it is difficult to find the root locus. So its importance is shown when the order of the system is 2. The root locus not only provides us the nature of the transient response, but it also represents the system stability for the range of k for where will be the system stable and instability range, and also if any oscillatory region. Before discussing the root locus in detail, two concepts that will be reviewed. The first is control system problem and the second is complex number representation as vector. The control system problem. The control system problem is already discussed in the stability video, that the roots, the pose of the forward transfer function is easy to find as compared to the closed loop poles. The open loop transfer function is defined as k, g of s, h of s. The pose of the forward transfer function are easily find because they are cascaded subsystems, and also variation in the k do not affect the location of any pole of the function, and are not all, and it is also not change the stability. So but the closed loop transfer function, using the closed loop transfer function formula, the pose of this characteristic equation is difficult to find, requires factorizing the characteristic polynomial, and also varying the parameter k changes the system behavior. Let us take an example. G of s is s plus 1 over s into s plus 2, whereas feedback is s plus 3 divided by s plus 4. The forward transfer function has pole at s is equal to 0, s is equal to minus 2, and s equal to minus 4. This is open loop transfer function, and these are the poles of open loop transfer function. The zeros are minus 1 and minus 3. For the closed loop transfer function, we need to solve this equation. We have entered the values of in the form of numerator and denominator. Applying simple calculus, we get this term. Entering the values, or we can directly enter these values here and solve. We can get this transfer function. Now we can see that this is third order system with a system parameter k. It can also not be solved using MATLAB because we have to define the value of k. So it is difficult to find the poles of this transfer function. The poles of transfer function t of s are not immediately known and are dependent on the value of k. The second problem, the second concept is vector representation of complex numbers. A complex number s is equal to sigma plus j omega described in Cartesian coordinates can be graphically represented using a vector with magnitude and angle. The complex number can also be described in polar form with magnitude m and angle theta. For example, we have a function s plus a. Substituting the complex number, we get that the real part a plus alpha plus j omega. Another complex number represented by a vector. We have just shifted the real part here. So real part will be sigma plus a. S plus a has 0 at minus a. So translate the vector a units to the left. This is another way to represent the vector. So this is alternate representation of the complex number that originates at 0 of f of s and terminates on sigma plus j omega. We conclude that s plus a is a complex number and can be represented by a vector drawn from 0 of the function to the point s. For example, this number is a complex number drawn from the 0 of function. Here we have 0 at -7. Drawing the vector from -7 to the number 5 plus j2, we get this vector. Valuation of f of s. F of s is the ratio of s plus z product of s plus z sub I, where I ranges from 1 to m, and denominator is the product of s plus pj, where j ranges from 1 to n. Magnitude of the vector can be found from the zero length over product of pole length, where s minus zi is a magnitude of vector drawn from the 0 of f of s at minus zi to the point s. Similarly, the pole length is a magnitude of vector drawn from the pole of f of s at minus p sub j to the point s. Similarly, this is the representation of the point in polar form. We have to find the magnitude and length, the angle. The magnitude is found by the ratio of zero length to the pole length, the product of all the zeros length, and divided by product of pole length. This magnitude will be found using the formula converting the Cartesian coordinates to the polar coordinates, like x square plus y square square root for each of the zeros and pole. Similarly, for angle, we have to find the zeros angle by using tangent inverse y over x, and all the zero angles will be found out and all the pole angles will be found out. The difference of these sum of pole angle, zeros angle minus sum of pole angle, will give us the angle of f of s. A zero angle is the angle of vector drawn from 0 of f of s at minus z to the point s measured from positive real axis, and a pole angle is the angle of vector drawn from the pole of f of s at minus p to the point s measured from the positive real axis. Now we will defining the root locus. Let us take a camera system that automatically follows a subject. The block diagram for this system is shown here. The controller part is amplifier and the plant is motor and camera. With this subsystem, solving for the closed loop transfer function, we get this term where k is the product of k1 and k2. As this is a second order system, we can manually change the value of k from 0 to some high value. Let's take in this case 50. For 0k, the nature of response is real overdamp and poles are real and unequal. At k is equal to 25, we get critically damped system, and further increasing k give us the underdamped response. So we can see that if we require critically damped response, we can now set the value of k to 25, or any other desired response can be selected from these values. But for higher order system, it is difficult to find manually, and we will need the root locus technique to draw this pole plot. Here root locus has been shown. At k equal to 0, we have roots at -10 and origin 0. Root move in this direction. At -5, it becomes now further increasing the value of k, the roots become complex conjugate and move in this direction. So we can see that regardless of value of gain, the real part of complex pole are always the same, since the settling time is inversely proportional to the real part of the complex pole. For this second order system, the conclusion is that regardless of the value of gain, the settling time for the system remains the same under all conditions of underdamped responses. Also, we increase the gain, the damping ratio diminishes and the percentage overshoot increases. The damped frequency of oscillation, which is equal to the imaginary part of the pole, also increases with an increase in gain, resulting in reduction of peak time. Finally, since the root locus never crosses over into the right half plane, the system is always stable regardless of the value of gain and can never break into a sinusoidal oscillation. These conclusions for such a simple system may appear trivial. What we are about to see is that the analysis is applicable to the system of order higher than 2. The root locus will allow us to make that association and will become an important technique in the analysis and design of higher order system. In the next video, we will discuss the properties of root locus and how to draw root locus for higher order systems. Thank you.